Hi, in this video I am going to discuss Edexcel IAL Unit 5 June 2020 paper. That is the same paper for October 2020 also. Okay, first question. A radiation detector is placed near a radioactive source and measures the count rate from the source. Different absorbers are placed between the detector and the source. The results are shown in the table. That means when there are no absorbers, the count rate, corrected count rate. Corrected count rate means from the count rate after you subtract the background count rate. That is called corrected count rate is 850 when there is no absorbers. When paper is kept also the same, no change. You know, paper can stop only alpha. So if there is no change, means the source is not emitting alpha. If the source emits alpha, there will be a drop in the count rate because paper will block it. No change in count rate means the source is not emitting alpha. But when aluminum foil is kept, there is a significant drop to 150 means beta is emitted. Aluminum blocks beta minus and alpha, but we know already there is no alpha, so there is beta minus. After that, when you keep lead sheet, it's again dropping to 20 means lead can drop, lead can block everything. Alpha, beta, gamma, everything will be blocked by lead. But we know that after you keep the aluminum foil, beta is blocked. So the radiation passing through it is most probably gamma, which is 150 count rate is giving. But when you keep a lead, it's dropping to 20 means there is gamma also. So the correct answer, the source is emitting both beta radiation and gamma radiation. There is no alpha. How do I know there is no alpha? No change in count rate when paper is kept. So the correct answer for question number 1 is D. Okay, question number 2, binding energy per nucleon against nucleon number graph is given. The graph shows how the binding energy per nucleon varies with nucleon number. Which of the following conclusions is supported by this graph? So this is about energy release or absorbed. But you know that during nuclear fission and nuclear fusion, energy will not be absorbed. There will be net in overall. Net means in overall energy will be released. So since overall energy is released, wherever they say about absorption, we don't need to consider. Statement B and statement D we don't need to consider because energy will not be absorbed in overall during fission and fusion. Energy will be released during fission and fusion. Okay, so we need to consider the statement A and the statement C. Okay, so how to find the energy release? We normally find in two different ways. For example, I'll take a fission reaction. Say for example, uranium nucleus absorb neutron, yeah, and it becomes barium, krypton, and emits 3 neutrons with energy release. How can we find the energy release? There are two different methods to find the energy release. First method we find by using mass deficit. We measure the mass deficit in this reaction equation. So mass deficit means mass of the uranium plus mass of this neutron minus mass of barium plus mass of krypton plus 3 times mass of neutron. This is the mass deficit in this reaction equation. Then the energy released during a fission, one fission reaction is equal to delta M times C square. This is one method. This is the first method. So this method we can't use here to answer this question. Second method, energy release is equal to this method we can use in both fission and fusion, right? First method we normally use in Edexcel to find the energy release by using the mass deficit in both fission reaction and fusion reaction. Second method we don't use much, right? But anyway, we can find the energy release by using binding energy. How do we find the energy release means? You know, whenever a nucleus is broken, energy will be absorbed. Whenever a nucleus is formed or created, energy will be released. So in this reaction equation, I can say the uranium nucleus is broken because there is no uranium after reaction. So the uranium nucleus is broken, so energy is absorbed. But barium nucleus is created, so energy is released. krypton nucleus is created. So there is energy release. So here the total energy release is given by neutron is an individual particle. It's not a nucleus. So there is no absorption or emission when neutron is created or neutron is absorbed. Whenever nucleus is formed, energy will be released. Whenever nucleus is broken, energy will be absorbed. So the net energy released during this fission reaction could be given as binding energy, B dot E, binding energy of barium. So barium is created, so energy is released, plus binding energy of krypton, because krypton is created, minus, this is absorbed energy. When the uranium is broken, energy is absorbed, minus binding energy of uranium. So this gives the energy release in fission reaction. Same way, for fusion reaction also, we can find the energy release either by using mass deficit method or binding energy of the product minus binding energy of the initial nucleus. That way we can find the energy released, the net energy released in nuclear fusion also. Right. Now look at here. When we consider this second method to answer this question, during fission reaction, you know barium, krypton, they are somewhere here. Their binding energy per nucleons are larger. Therefore, the energy release will be larger. We are adding the binding energies of barium, krypton, then we are subtracting the binding energy of the uranium. But all those values are larger, so the final energy will be larger. But when we think about fusion, where hydrogen somewhere here, helium somewhere here, already their binding energy per nucleons are very small, their nucleon number also very small, therefore binding energy will be very small. So there when we find the energy release by using this method for fusion reaction, the energy release will be very small. I hope you understood. So the correct answer for question number 2, during fission reaction, large amount of energy will be released. So the total energy release greatest when mass nucleus undergoes fission reaction is the correct answer, which is C. Question number 2, correct answer C. Okay, question number 3. Question number 3. A closed container holds a mixture of two gases at a constant temperature. Each molecule of gas X has mass 4 times the each molecule of gas mass Y. So mass of X is 4 times mass of Y, they are telling it. What is the ratio of RMS velocity of molecules in gas X divided by RMS velocity of molecules in gas Y? We know that the RMS speed, we have only one equation. The average kinetic energy of a molecule, half mc squared, equal to 3 by 2 kT. So these two molecules X and Y have different mass, but both are at the same temperature. So both molecules will have the same average kinetic energy because they are at the same temperature, but they have different mass, means they'll have different mean square speed. So when I consider for mass Y, if I consider for the gas Y, I can get half my cy squared equal to 3 by 2 kT. For X, if I consider half mx cx squared equal 3 by 2 kT. But instead of mx, I can write 4my. So I will replace this by 4my equal 3 by 2 kT. Both gases are at the same temperature. So the average kinetic energy of both gas is the same. Average kinetic energy of a molecule of X and average kinetic energy of molecule of Y have the same kinetic energy. Therefore, the left side should be same, that is half my cy squared equal to half my, so mx, that should be 4 times my cx squared. Okay, so we need to find the ratio of RMS velocity of molecules in gas X. So I need to divide this by this. So that means half will get cancelled. I can say cx squared over cy squared equal to half got cancelled, my got cancelled, cx squared over cy squared will be 1/4. If you take both sides square root, because RMS speed, they are comparing the ratio of RMS speed, not the mean square speed, root mean square speed. So both sides I need to take the square root of it. That is RMS speed. It will become 1/4 will become half. So the correct answer for question number 3 is B. Okay, this circuit diagram is given. This question related to unit 2 electricity. The negative temperature coefficient thermistor, you know, when the temperature decreases, its resistance will increase. The question is related to something like that. The temperature of the thermistor decreases. Select the row of the table that shows how the readings of the voltmeter ammeter changes. You know that when the temperature decreases, resistance RT, the resistance RT, I can call RT for thermistor. So when the temperature decreases, T stands for temperature, resistance RT will increase. So the same EMF, no change in EMF. So the voltmeter reads the voltage across it. So the same voltage will be divided across the thermistor and the standard resistor at the ratio of their resistance. So this resistance remains unchanged. This resistance is increasing. So voltage across it will increase. So voltage across the resistor, the voltage across this one will decrease. Voltmeter will decrease. Also, the resistance is increasing, so the total resistance of the circuit is increasing, so current flow also will decrease. So question number 4, correct answer A. Question 5, a simple pendulum takes 1 second to swing from one extreme position to the other. That means half the period. Is it? So it's oscillating from this position to this position. For that it takes 1 second, means T by 2 equal 1 second. The question is, which of the following expressions give the length of the pendulum? Simple, the equation is given in the data sheet. T equal 2 pi square root of L over G. So from this we can say the time period is 2 seconds. So 2 seconds is equal to, they are giving it in 2 decimal points, or 2 seconds is equal to 2 pi square root of L over G. So square both sides, 2.00 squared over 4 pi squared is equal to L over G. So L is equal to cross multiply 2.00 squared into G over 4 pi squared. Correct answer B. Okay, question 6. The student used a Geiger-Müller tube to measure the background count for 10 minutes. Then she used the apparatus below. They are giving a diagram of Geiger-Müller tube, lead absorber, gamma source, everything as a diagram. So she then used the apparatus below to measure the count for 2 minutes. So background count is measured for 10 minutes. Now the count by using a gamma source is measured for 2 minutes. So to correct the readings for the effect of background radiation, what should we do? Okay, now if we are measuring the background count and the count from the source for the same time period, say for example, if you are measuring the background count for 10 minutes and the count with the source also 10 minutes, there you can subtract this background count from the count with the source to do the correction. But here what's happening, this is measured, the background count is measured for 10 minutes, the count with the source is measured for 2 minutes. So you can't subtract because they are different times. So there we need to find the count rate. So count rate. So here you should find the count rate by dividing the total count by 10. Find the count rate. Here find the count rate. Dividing the total count by 2 minutes. Or if you want to count for seconds, convert this to seconds. Convert this to seconds. Find the count per second. Count per second. Then from this count per second, subtract this count per second. Okay. Okay, so normally we do that way because when you are doing practical, it's difficult to measure the count for exactly the same time, the background count and the count with the source. We can't measure for exactly the same time. So what we do, we measure for different times. Background count we might measure for 15 minutes. Count with the source we measure for maybe 1 minute. But in both we measure the count rate, background count rate and the count rate with the source. Then subtract the background count rate from the count rate of the source. We will do the correction. Okay, so question number 6, correct answer, subtract the background count rate from each count rate. So correct answer for question number 6 is D. Okay, question 7 again about radioactivity count rates. The student discovered that the thickness of 1 centimeter of lead reduced the corrected count rate to 50% of its initial value with no lead. So when there is no lead, there is a particular amount of count rate. When you keep 1 centimeter, the count rate dropped to 50%. That means 50% is absorbed. Which of the following statement is correct? The thickness of 5 centimeter would reduce the count rate to 75% of its initial value. So that means the thickness of 5 centimeter would reduce the count rate to 75% of its initial value, means 0.5 centimeter will make it absorb. It says it's actually, one thing you should know that, so this absorption depends, actually related by an exponential relationship. Say for example, if there is a gamma source and if you use a lead sheet, the intensity of the gamma radiation will reduce according to I equal I naught e to the power minus mu x. Not in your syllabus, this equation is not in your syllabus, where x is the thickness of the lead sheet and mu is called attenuation coefficient. Anyway, so the this is for the gamma radiation. Same way for count rate also will decrease exponentially. So if the first statement is correct, that means thickness of 5 centimeter would reduce the corrected count rate to 75%, means it absorbing only 25%. That means 1 centimeter thickness absorbs 50%, absorbs 50%. 0.5 centimeter absorbs 25%. That's the reading. That's the reason reading becomes 75%. So if this is correct, that obeys linear relationship. So it's not obeying linear relationship. It's obeying exponential relationship. Remember that it's exponential. You don't need the equation, but not linear. It's an exponential. Same way, if you was using 2 centimeter, absorption will be 100%. The count rate will become 0. If it is a linear, but it's not a linear, therefore it's not a linear, it's an exponential. Therefore the statement A is wrong, because it's, if it say that is correct statement that obeys linear relationship, it's not linear, it's an exponential relationship. The equation is not in your syllabus, but no, you must know that it's an exponential relationship. So answer A is wrong because it's not linear relationship. Answer B, 0.5 centimeter would reduce the count rate to 25%, means when you are reducing the thickness, absorption is 75%. That won't happen, is it? When you are reducing the thickness, absorption is increasing. That's the reason count rate become 25%. That also wrong statement. Answer D, the thickness of 2 centimeter would reduce the count rate to 0. That is true if you are using linear relationship. It's not linear relationship. So answer A, answer B, answer D are not acceptable. So the only answer is C. The correct answer, C. So here we are eliminating the answers. We don't have the equation, not in your syllabus, but we can eliminate the answer A, because answer A, if it is correct, the relationship should be linear, but we know it's not linear. Answer B is not acceptable because when the thickness decreases, absorption becomes 75%. That's the reason count rate becomes 25%. So can't happen. When the thickness reduces, it can't absorb more. So that also wrong statement. Answer D is not acceptable because if it obeys linear relationship only, 2 centimeter will absorb 100%. The count rate will become 0. So that also wrong. So the only correct answer is C. Okay, question 8. A solid is heated and it melts at constant temperature. Which row of the table shows how the kinetic energy and potential energy of the molecules changes as the solid melts? Okay, so it's something related to internal energy. You know, internal energy is the sum of average kinetic energy and potential energy of the substance. The kinetic energy depends on temperature. When the temperature increases, the average kinetic energy of the molecules will increase. When the temperature decreases, average kinetic energy will decrease. But the potential energy does not depend on the temperature. Potential energy changes only during state change. Only during state change, potential energy will change. For example, when solid becomes liquid, during melting, potential energy will increase because heat is supplied to break the molecules. The intermolecular force will be broken, so work is done on it, so the potential energy will increase. But during the state change, there is no change in kinetic energy. That's the reason temperature remains constant. So remember that during state change, potential energy changes. For example, when solid becomes liquid, potential energy will increase, but no change in temperature, so no change in kinetic energy. So the here, the which row of the table shows how the kinetic energy and potential energy of the molecules changes at the solid melts. During melting, no change in temperature, so no change in kinetic energy, but the potential energy will increase because solid is becoming liquid. You need to do work to break the bonds, so work done will be stored in it in the form of increase in potential energy. So the correct answer for question number 8 is C. Question number 9. A student hangs a mass from the end of a spring and sets the mass into vertical oscillation. The period of oscillation of the mass is capital T. The student then hangs the same mass from a second spring with the spring constant 4 times the first spring. What is the spring period of oscillation of the second spring? So we know the equation for time period T equal 2 pi square root of m over k. For the second spring, the time period will take it T1, 2 pi square root of the same mass is attached m over 4k because spring constant is 4 times. So this I can write mathematically. The 4, when I take it outside of the square root, it will become half times 2 pi square root of m over k. 2 pi square root of m over k is t. So T1 equal t by 2. The correct answer B. Question number 10. Forcing a system into oscillation may result in resonance. For resonance to occur, the oscillating system must be driven at its natural frequency. So that's very basic principle regarding the resonance. So it should be resonate at its natural frequency. So question number 10, correct answer A. Correct answer A for question number 10. Okay, section B, question number 11, structure type. Electrostatic forces and gravitational forces can both be modeled by the idea of a field. Give one similarity and one difference between electric field and gravitational field. Okay, similarity, you can say both obeys or both follows inverse square law. So in gravitational field, the force between two masses is given by F equal G m1 m2 over r squared. In electrostatic force, electric field, the electrostatic between two point charges is given by F equal K Q1 Q2 R squared. So both obeys inverse square law because their force depends on 1 over R squared format. So similarity, both obey inverse square law. Differences. So we need to give one similarity and one difference. So the difference we can say the electric field or electrostatic force could be attractive or repulsive, but gravitational force is always attractive. So that's the difference. Question number 12. Massive planet orbits the red dwarf star. The planet was discovered after wavelength shifts in spectral lines were seen in the light received from the star. A part, explain how the massive planet orbiting the star can cause the change in wavelength of the light received from the star. Okay, so we can say like this, A part, there's a massive, there's a star This is a star, and there's a massive planet is orbiting. So this is the Earth. We are observing the star from the Earth. Okay, so what happens? The planet is massive. So the planet, if it is massive planet, when it is here, it will pull the star little closer to it due to the large gravitational force exerted by the planet on the star. The star would be somewhere here due to the larger gravitational pull exerted by the planet. When the planet is here, the star will be pulled somewhere here. The planet will pull the star to this position. Same way, when the planet is here, it will pull the star to this position. When the planet is here, it will pull the star to little bit towards it. Same way, when the planet is here, the star will be pulled towards it. So we are observing the star from Earth. So what's happening? Relative to us, the star velocity is changing. The position of the star is changing relative to us, and the velocity of the star is changing. So when the velocity of the star relative to us on from Earth, when we observe it is changing, means there will be change in wavelength due to Doppler effect. Okay, so that's the reason the question is explain how the massive planet orbiting a star can cause change in wavelength of light received from the star. So received from the star, we are observing from Earth somewhere here. So the light we are getting from the star will change because star is in motion. Star is not at rest. Star is in motion because of the larger gravitational pull exerted by the planet. If the planet is lighter, normally Earth can't exert such larger force on Sun because Earth is not that massive. But this planet, if it is massive planet, it can exert gravitational pull on the star and pull it towards it little bit. That will cause the planet, that will cause the star to change its velocity when we observe from Earth. So there will be change in velocity relative to us, means according to Doppler effect, there will be change in wavelength we receive, the radiation received from the star. Okay, B part, the maximum shift in the spectral line of wavelength 4.35 10 to the minus 7 meter in the light received from the star 876 is 3.19 10 to the power minus 13 meters. So the change in wavelength for 4.35 10 to the power minus 7 meter wavelength is given. So delta lambda and lambda both are given. So calculate the maximum velocity. So nothing, we can use the Doppler effect equation. Delta lambda over lambda equal V over C. Delta lambda is given 3.19 10 to the power minus 13. The lambda is given 4.35 10 to the power minus 7 equal V over C 3 into 10 to the power 8. Find the V, that will be 220 meter per second. Okay, question number 13 that appeared several times in the past papers. Scientists have been working to achieve a practical or nuclear fusion reactor for more than 70 years. So far, this has been with only limited success. Explain the difficulties involved with fusion as a viable source of power on Earth. You should include reference to the conditions necessary for fusion to occur. So you know that during fusion, the hydrogen nuclei should almost touch each other. So there will be much larger electrostatic repulsive force. You know, if you think about F equal K, Q1, Q2, R squared, when two hydrogen nuclei touches during fusion, they should melt together, they should touch each other, the distance become almost zero, so the electrostatic repulsive force will be very large. So due to that much higher electrostatic repulsive force, they will be bounce off. So to avoid it, they should carry much larger initial kinetic energy to overcome the electrostatic repulsive force. To get such much larger, higher kinetic energy, the temperature, you know, hydrogen gas, the temperature should be kept at very high value. So what's the problem? When you are keeping the temperature at very high value, the heat loss to the surrounding, if the plasma touches the container or the material touches the container, it will lose large amount of heat to the surrounding. So the heat will be lost and the fusion will be stopped. That's the problem. The next problem is to continue the fusion reaction, the rate of collision should be much higher. To have such higher rate of collision, the density concentration or the density should be kept very high. So keeping that higher density also very difficult. So the difficulties here, first one is we need much larger temperature, much higher temperature to provide larger kinetic energy to the hydrogen nuclei to overcome the electrostatic repulsive force. Second one, the density has to be kept much higher to have higher rate of collisions to sustain the fusion reaction. Next one, to avoid some problems like contaminant problems, the stronger magnetic field is required. So the stronger magnetic field is required to keep the molecules together. So on Earth it's difficult to get such much stronger magnetic field. So these are the difficulties in controlled fusion reaction. Okay, question 14. The mean intensity of solar radiation arriving at the Earth is 1.37 kilowatts per meter squared. So radiation, solar radiation at Earth is, that means the intensity, right, or radiation flux. A part, the density of the Earth from, the distance of the Earth from the Sun is 1.5 10 to the power 11 meter. Show that the luminosity of the Sun is about, so we know the equation I equal A part, I equal L over 4 pi d squared. So intensity, we know that 1.37 10 to the power 3 equal L over, we need to find the L over, the distance is given as 1.5 10 to the power 11. So 4 pi into 1.5 10 to the power 11 all in squared. Find the L. So 3.87 10 to the power 26 watts. Luminosity means power of the radiation. Okay, B part, that's the answer for A part. B part, question number 14. Energy radiated from the sun results in a decrease in the mass of the sun. So you know the energy is released, you know, according to special theory of relativity, energy has equivalent mass, so mass will be released, the mass of the sun will decrease. Calculate the decrease in mass of the sun due to this radiation over one period of year. Okay, so he can say total energy released in 1 year. So this is the energy released, the radiation, the power released per second. You know, energy released per second is the power. Energy released during 1 year, that is equal to power, luminosity into time. So that is 3.87 10 to the power 26 into 1 year. This is per second, joule per second. So 1 year is given as 3.15 10 to the power second. So multiply 3.15 10 to the power 7 seconds. So that's a joules, energy released in during 1 year. So that's going to be 1.22 10 to the power 34 joules. So this is the total energy released. So we need to find the equivalent mass of this energy. E equal delta M times C squared. So 1.22 10 to the power 34 equal equivalent mass or the mass released in c square 3 into 10 to the power 8 all things square. So the mass released or lost by the sun is going to be 1.36. Divide this by this, 1.36 into 10 to the power 17 kilogram is the amount of mass lost by the sun during 1 year. Okay, question 15. The graph shows how the gravitational field strength G of the Earth varies with distance r from the center of the Earth. R is given in multiples of radius RE of the Earth. And your distances from the center is given in terms of multiple of radius of the Earth. Okay, so there's a graph given, y-axis G, x-axis the distance from the center of the Earth in terms of radius of the Earth. Show that G obeys inverse square law. So if you, that's nothing. So if you are given a graph y against x, the graph is something like this shape. And if you also check whether it obeys inverse square law means y proportional to 1 over x squared. That is y equal k times 1 over x squared. Y x squared should be a constant. So if you take 3 different points from the graph, this is x1, y1, y2, x2, same way y3, x3. If you find y1 times x1 squared, y2 times x2 squared, y3 times x3 squared, you should get the same constant. The constant should be the same. If you get the almost same constant, that means y is inversely proportional to x squared. That's the relationship we use normally to show y proportional to x squared format. Here the y-axis is G and x-axis is R in terms of RE. So we'll take 3 clear points from the graph. I took R1 equal RE. When R1 equal RE, I can say G1 R1 squared, G1 R1 squared is equal to G, that is 9.81. You can see it from the graph. When R1 is equal to RE, that is 1.0. If I take 1.0 means R equal RE. So that is 9.81 RE squared. So yeah, so I can say 9.81 RE squared. So when R2, so second reading is equal to 2 RE when I take it from the graph, G2 R2 squared, do it from the graph, G2 R2 squared is equal to 2.4, that's the G value is 2.4 into 2 RE, 2 times RE squared. So that's going to be 9.6 RE squared. Same way when I take R3 equal 3 times RE from the graph, that is G3 R3 squared equal G3 value from the graph when the radius or the distance is 3 times RE from the graph. So 3.0 there, the G value is almost 1.1 times 3 RE squared. So that's going to be 9.9 RE squared. So G1 R1 squared is 9.81 RE squared. This is 9.6 RE squared. This is 9.9 RE squared. So almost the same value I am getting. G1 R1 squared, G2 R2 squared, G3 R3 squared. All are in terms of RE squared 9.81, 9.6 RE squared, 9.9 RE squared. So almost these values are same. Therefore, it obeys inverse square law. We can say therefore it obeys inverse square law. G obeys inverse square law. Okay, see the graph. The graph is something like this. So 1.0, you can say it's meeting at 9.81. You can see the graph. This is the G graph. This is 9.81. When 2.0 they are giving R, RE. So 2.0 means value of R 2.0 RE. That time you can see the G value is 2.4. When 3.0 means R equal 3.0 RE. So that time the R G value is 1.1. So those are the values I used here. Okay, question 15 part B. A satellite is launched from the surface of Earth into an orbit a height 5 times radius of Earth, 5 RA, above the surface of Earth. The change in gravitational potential energy of mass m when it experiences vertical displacement delta h can be calculated using the expression mg delta h. We learned that in unit 1. State why this expression cannot be used to calculate the change in the gravitational potential of the satellite. That is the first part, B part. You know, the G is not constant. So how do we use that in unit 1? Okay, I'll go a little out of this question, but that is in your syllabus. Based on your syllabus, little bit I'll show that. Say for example, this is a planet, say Earth or whatever it is. The gravitational field, the radius of the planet is capital R. So the gravitational field strength on the surface of planet is G. So in unit 1 we learned that if you throw a ball vertically upwards at a particular speed, the gain in GP we say mgh, right? So when the ball is released or thrown from a surface of Earth at a particular velocity, when the ball moves to a height h, here we say that gain in GP is mgh, but here they are saying why can't we use that equation? So you know the gravitational potential energy is given by, so the gravitational potential of a mass or gravitational potential created by a planet is given by V equal minus Gm over R. R is the distance from the center of the planet, M is the mass of the planet. Why there is negative sign? They can ask. The reason negative sign is, you know, gravitational force is always attractive. That's the reason the gravitational potential is negative. Okay, so the gravitational potential energy of the object which has mass symbol m is given by, say if it is at a particular distance from the center of the planet, at a distance r, the gravitational potential energy is given by gravitational potential times mass of the object. So the gravitational potential energy of the object is given by gravitational potential times mass of the object. So that is going to be minus Gmm over R. At a distance r, the gravitational potential energy of the object is given by minus Gmm over R. So if the object is moving from surface to a point where the height is h, the gravitational potential energy gained by the object is given by final gravitational potential energy minus initial gravitational potential energy, that is the gain in GPA, right? What we used in unit 1, I'll get the equation from this gravitational field theory. So gain in GPA equal final gravitational potential energy minus gravitational potential energy on the surface of the planet. So it is moving from this point to this point. This is at a height h from the surface of the planet. So GPE, the gain in GP equal final gravitational potential energy, that is minus Gmm over final gravitational potential energy minus Gmm over R plus h minus initial gravitational potential energy on the surface of the planet minus Gmm over R. Okay, so solve it. Minus into minus plus, you will get Gmm over R minus Gmm over R plus h. Okay, that's the gain in gravitational potential energy. So continue. This is given by Gmm 1 over R minus 1 over R plus h. Solve it further. Gmm over within bracket, take LCM as R into R plus H. So R plus H minus R over R into R plus H. So that's going to be GMM into R plus H minus R, H over R into R plus H. Okay, now only we are going to do the approximation. In unit 1, we don't consider much larger distances. Say, if the radius of the planet is R and the height is H, and if the H is very much smaller, if H is very much smaller compared to radius of the planet, say if H is very much smaller compared to radius of the planet, then we can say R plus H approximately equal to R. You know that, simple mathematics. If the H is very much smaller compared to radius of the planet, say when you consider Earth, radius of the Earth is almost 6,400 kilometer. 6,400 kilometers. So when you throw a ball, if it moves, or even a bullet is fired, if it goes even 5 kilometers above the surface of Earth, even 10 kilometers if it moves above the surface of Earth, 10 kilometer is much smaller compared to 6,400 kilometer. So there we can assume R plus H approximately equal to R. So if we take, so if I can say when H very much smaller than R, then R plus H approximately equal to R. So there I can say gain in GPE, delta GPE, gain in GPE is going to be mgmm within bracket H over R times R plus H is almost equal to R, so R squared. GMM H over R squared. But we know that the gravitational field strength on the surface of Earth, gravitational field strength on the surface of Earth is given by G equal Gm over R squared. Gravitational field strength on the surface of Earth is given by Gm over, where m is the mass of the planet, Gm over R squared. So here Gm over R squared, I can rearrange this equation, Gm over R squared, Gm over R squared into here m times h, this h. So this is G gravitational field strength. So it's going to be, what is it, GMH means mgh. So that's the thing you learned in unit 1, gain in GP, mgh. So here we can use this only when G is constant. G is constant means when that happens, when the distance it moves is much smaller than the radius of the Earth, then the G will remain constant. In that situation, we can say gain in GP equal mgh. So in this question, the object is thrown to 5 times the radius of the Earth, much larger distance from the surface. So there we can't assume the gain in GP mgh, we can't assume because the distance it's moving is much larger. So G has very much larger variation. Okay, so the answer for B part, first part, state why this expression cannot be used to calculate the change in gravitational potential energy of the satellite. Answer should be, since the height is much larger than radius of the Earth, the gravitational field strength G is not constant. That's the answer. Since the height moved by the satellite, which is 5 times radius of Earth, much larger than radius of the Earth, therefore G, symbol G, is not constant. That's the answer. I am not writing it on the board. You can write it. Okay. Okay, question number 15, B part, second part. Calculate the change in gravitational potential energy of the satellite. Mass of the Earth is given, radius of the Earth is given, mass of the satellite given. So I already told that. So change in GPE, we have to find it. So delta GPE equal minus GMM over R2, we'll substitute R2 minus GMM over R1. So final distance is the radius of the Earth is RE. Radius of the Earth is RE. Its height is 5 Re. The satellite is orbiting at a height of 5 Re. So from the center, from the center O, the distance is 5 Re plus Re, 6 Re. So 6 Re is R2. So we'll solve it further. R1 is surface of Earth. R2 is the final position where it is orbiting. It was launched from the surface of Earth. So initial position is R1. R1 is equal to Re. And R2 equal to 6 Re. 5 Re is the height. Radius of the Earth is Re. So Re plus 5 Re, 6 Re. So substitute all these things. You will get the final answer. All are given, all data given there. So minus into minus plus. So G mm over R1. G mm over R1 is Re. Minus G mm over 6 Re. R2 is 6 Re. So it's not a big issue. G mm over Re, we'll take it out. 1 over 1 minus 1 over 6. Okay, so solve it. So that will be 6 minus 1, 5. 6 minus 1, 5. 5 GMM over Re. Okay, 5 times G we know 6.67. 10 to the power minus 11. Mass of the Earth is given 6 into 10 to the power 24. Mass of the satellite, symbol M, is given as 3.5 10 to the power 3. Radius of the Earth is given 6.4 10 to the power 6 joules. You will get it 1.82 10 to the power 11 joules. That's the answer. Okay, question number 6. Anlilam and Mintaka are stars in the constellation of Orion. The table gives some information about these stars. So they are giving the surface temperature, luminosity and distance from the Earth. Okay, so how to identify whether a given star cluster or star belongs to main sequence or white dwarf or red giant? It's like this. You know the HR diagram, in the Hertzsprung-Russell diagram, the y-axis is relative luminosity, L over L sun, and x-axis is the temperature in Kelvin. Normally the temperature is marked from in the decreasing side. Say for example, if the temperature is starting from somewhere like 40,000, so 20,000, 10,000, normally in that order, factor half, then 5,000, 2,500 we can mark here. So the main sequence is somewhere here. And sun is somewhere here, so this position will be 1. Relative luminosity will be 1 here. So there 10 to the power minus 2, 10 to the power minus 4 can go here, 10 to the power 2, 10 to the power 4 can go. Right. Okay, so when they are giving a star or star cluster with something like their luminosity is larger, something like 10 to the power 2 order. 10 to the power 2 order. Luminosity is 10 to the power 2. But at the same time, temperature is lower than 5,000. 10 to the power 2 lower than 5,000. Somewhere here, that means that is red giant. Normally, generally I am saying if the luminosity L over L naught approximately somewhere 10 to the power 2 order, that is 160, 180, 200, 300, something like that. And the temperature lower than 5,000, something like 4,800, 4,000 or 3,000, something like that. Then it's going to be something like 1,000, like a 3,000 or 3500, something like that if they tell. That is red giant. Same way, the relative luminosity L over L naught is something like 10 to the power minus 2, 0.01. In that order, if they give, and the temperature is more than 5000, something like 7000 or 8000, something like that, if it is given, that will be white dwarf. Somewhere here, it's going to be white dwarf. Otherwise, if it is temperature higher, relative luminosity also higher, means it's a main sequence massive star. Temperature lower, luminosity also lower, something like temperature is something like 160, and relative luminosity is something like 160, 180, and the temperature also something like 3600. That also low mass main sequence star. Okay, so you should be able to identify luminosity lower, temperature lower, most probably it's a main sequence low mass star. Temperature is higher, relative luminosity also much higher, main sequence massive star. Temperature is uh, temperature is higher, relative luminosity is lower. That is higher means something like between 5000 to 10,000, 5000 to 12,000, like that. And the luminosity is lower than 1, that is white dwarf. Then temperature is lower, something like 4000, 3000 in that order, but the luminosity is around 100, 150, 200, like that, that is red giant. So you should be able to identify these things. So based on that, question number 16, there's a table. You can see for both stars, Mintaka and Alnilam, both the surface temperatures are much larger, luminosity, relative luminosity also much larger. The question is, state where these stars would be located on the HR diagram. They are massive stars in the HR diagram, so they are main sequence stars on the left upper corner of the main sequence. So the answer for question number 16, A part, these are massive main sequence stars. They should be on the left upper corner of the main sequence on HR diagram. That's the answer for question number 16, A part. Okay, question number 16b part, calculate the wavelength at which peak radiation power occurs for Mintaka. So that is Wien's law. We need to use Wien's law, lambda max T into T equal 2.898 10 to the power minus 3 meter Kelvin. So lambda max, I need to find it. So the temperature is given for Mintaka is 3 into 10 to the power 4 equal 2.898 10 to the power minus 3. So find the lambda max, that's all. That will be equal to 9.66 10 to the power minus 8 meters. C part, calculate the radius of alnilam. So radius, so the equation that relates the radius and luminosity are given. Steffan Boltzmann equation, L equal sigma A T to the power 4, and we know that A equal 4 pi r square for a spherical shaped star. So everything we know that we need to substitute there. So L is given as for alnilam is 5.37 10 to the power 5 is the relative luminosity over luminosity of sun. So relative luminosity of that particular star is 5.37 10 to the power 5. To find its actual luminosity, we should multiply 5.37 10 to the power 5 by the luminosity of the sun. We should multiply. So L equal to relative luminosity is 5.37 10 to the power 5 given on the table, multiplied by the luminosity of the sun given below the table, 3.85 10 to the power 26 equal sigma Steffan Boltzmann constant is 5.67 10 to the power minus 8 times 4 pi r squared is the surface of the spherical shape object into T to the power 4. Temperature is given for alnilam 2.75 10 to the power 4 to the power 4 t to the power 4. Okay, so solve it. You'll get the radius r is equal to 2.25 10 to the power 10 meters. Okay, part D, question number 16. Deduce which of these stars gives the lower intensity of radiation on the Earth. So the distance of these two stars from the Earth also given. So not a big issue. L equals we can use I equal L over 4 pi d squared. Is it? We can use that equation. Intensity is equal to luminosity of the star over 4 pi d square. Luminosity of the star, we can get it from the relative luminosity is given, multiply the relative luminosity by the luminosity of the sun. So individually find the intensity of the alnilam on surface of Earth, intensity of the Mintaka on the surface of Earth. You have to use the proper distance of those stars from the Earth. Simple question. So I can say intensity of alnilam A, that is equal to luminosity. I can say the luminosity is 5.37 10 to the power 5 multiplied by luminosity of sun is given. I can solve it. Without solving also I can find another method. 4 pi d square, distance of it from the Earth is 1.90 10 to the power 19 squared. You can solve this one, or without solving I can divide and find which is larger. Is it? Either way I can solve it. Directly I can solve this. Substitute the value of luminosity of the sun is given as 3.85 10 to the power 26. Solve it. You will get the direct answer for this one. Same way I can find it for Mintaka M. So L is luminosity is for the Mintaka is 9 into 10 to the power 4 into luminosity of sun over 4 pi. The distance of it is 8.70 10 to the power 18 all things squared. Okay, so I can solve them separately and find which is the highest value. Okay, but instead of doing that, I can do this way also. I can divide which is larger, which is larger. So I can find IA over IM, IA over IM if I find it. Anyway, that's not a big issue. You can find this value, you can find this value, you can give the conclusion, no problem. But to reduce the working, IA over IM, so LS, SLS will get cancelled, 4.4 will get cancelled. So you will get it 5.37 10 to the power 5 over 9 into 10 to the power 4, this value, 9 into 10 to the power 4 into, this will go up when I divide by this way, 8.7 10 to the power 18 over 1.9 10 to the power 19 all things square. So here is a square, here is a square. Anyway, you can do this way, find this one separate and you can give the conclusion. Or this way do it. So finally you will get 1.25. So that means IA greater than IM. So IA greater than IM means the question is deduce which of these stars give lower intensity on the means Mintaka will give the lower intensity. So Mintaka on Earth. Okay, question number 17. According to the Football Association rules, the football used in a professional match should have a circumference of 68 centimeter and 70 centimeter in between. The pressure of the air in the football must be between 60 kilopascal and 110 kilopascal above the atmospheric pressure. Means it could be more than atmospheric pressure 60 or 110, in that range, more than the atmospheric pressure. So A part, football was inflated with air at a temperature of 16 degrees Celsius. When inflated, the circumference of the football was 68.5 centimeter and it contained 2.5 10 to the power 23 molecules of air. Deduce whether this football met the FA rules. Atmospheric pressure also given. So we'll use P equal NKT and we'll find the pressure. Only thing we need to find the volume, 4 by 3 pi r cube. So we'll use the equation, question number 17. A part, PV equal NKT and we know volume equal 4 by 3 pi r cube. Okay, so here we need to find the volume, but only thing the radius is given. So from first we'll find the radius by using pi r square, 2 pi r. So we'll find that one first. 2 pi r is the rate circumference, that is 68.5 centimeter convert to meter. From that find the r. So r is going to be 0.109 meter. Then volume will be 4 by 3 pi r cube, we know that. We'll use the equation PV equal NKT. So we'll find the pressure. So P is going to be NKT over V. And we know that P equal 4 by 3 pi r cube. So we'll find the P. N is given 2.50 10 to the power 23. We know the K, Boltzmann constant, 1.38. 10 to the power minus 23. Temperature given 16 degrees Celsius, convert to Kelvin, plus 273 plus 16, that is 289 in Kelvin, over volume 4 by 3 pi r cube, 0.109 cube. Find the P. So the pressure is going to be 1.84 10 to the power 5 Pascal. So we have to compare with a kilopascal. So they are saying pressure could be 60 to 110 kilopascal above the atmospheric pressure. Atmospheric pressure given as 105 kilopascal. So when you convert this to kilopascal, it's going to be 184 kilopascal. So atmospheric pressure, we know that is 105 kilopascal. So excess pressure equal 184 kilopascal minus atmospheric pressure is 105. So that is going to be 79 kilopascal. But according to the rule, FA rule, it says it could be somewhere between 60 kilopascal to 110 kilopascal. So this excess pressure or I can say like this, rather than writing this way, I can say 79 kilopascal is less than 110 kilopascal, greater than 60 kilopascal. So it's falling within the range prescribed by the FA association, football association. So the questions deduce this football met the FA rules. Yes, it met the rules. Okay, question number 17B part. The pressure inside the football decreases as the temperature of the air inside falls. The volume of the ball remains constant. Explain why in terms of the motion of the ball. So the pressure inside the ball decreases when the temperature decreases. So you can say when the temperature decreases, Average kinetic energy of the molecules will decrease. You know, average kinetic energy is given by 3 by 2 kT. So average kinetic energy of the molecules will decrease. So when the average kinetic energy decreases, momentum of the gas molecules will decrease. You know, kinetic energy equal p squared over 2m. So when the average kinetic energy decreases, the average momentum of the gas molecules or gas particles will decreases. So during collision, the rate of change of momentum will decrease. So force exerted by the gas particle during collision will decrease. Therefore, force per unit area pressure will decrease. Okay, question 18. A reaction equation is given. A part complete the equation for the reaction, so it's not a problem. You can check the mass number 48 to 149 if you add it. And to balance it, you know, neutron 1 0, so there should be 3 neutron. I'm not doing it very simple O level type, so it's 3 neutron. Okay, so that's a part complete the equation. B part, the calcium ions were accelerated to an energy of 245 mega electron volt. State how ions of this energy could be produced by using particle accelerator. So accelerate the ion by using particle accelerator. Accelerate the ion by using particle accelerator. That is the answer for question number 18, part B, first part. Second part, question number 18, part B, second part. It is claimed that the calcium ion with an energy of 245 mega electron volt are traveling at relativistic speeds. Assess the validity of this claim. Mass of calcium ion is given as 47.95 U. Okay, so use it's claimed that a calcium ion's average energy gain. So convert the mega as 5 marks, too much actually. Simply you can do that. Question number B, part B, second part. Kinetic energy is given as 245 mega electron volt, that is 245 mega 10 to the power 6 into 1.6 10 to the power minus 19 joule. So kinetic energy means half mv squared equal to 145 into 10 to the power 6 into 1.6 10 to the power minus 19 joules. So the only thing we need to find the speed. Half into mass of the calcium ion is given 47.95 unified atomic mass unit. You can get it from the data sheet. 1 U equal 1.66 10 to the power minus 27. That's some conversion of U to kilogram. P square equal this value 245 10 to the power 6 into 1.6 10 to the power minus 19. So find the V, that is 3.14 10 to the power 7 meter per second. Okay, so it is claimed that the calcium ion are traveling at relativistic speed. So find what percentage of speed of light. This is 3 into 10 to the power 8 is the speed of light. Okay, you can find what fraction. So V over C equal 3.14 10 to the power 7 over 3 into 10 to the power 8. So that is 0.1 around 0.104. So it's not relativistic. So the question is, it is claimed that the ions with energy this much are traveling at relativistic speed, so not at relativistic speed. Okay, part C, the isotope Og294 is extremely unstable and decays via alpha decay. After 2.5 milliseconds, a sample contains 500 atoms of Og294. Calculate the original number of Og294 atoms in the sample. Half-life is given. So we can use n equal n naught e to the power minus lambda t. So first we need to find the half-life. So t half equal to ln2 over lambda. So we'll find t half is given as 0.89 millisecond, 10 to the power minus 3 equal ln2 over lambda. From that, lambda is equal to 778.8 per second. Then we use n equal n naught e to the power minus lambda t. So n is 500. How much it had earlier? We need to find the n naught e to the power minus 778.8 into time is 2.5 millisecond. 2.5 10 to the power minus 3. So solve it. You know how to solve it by taking natural logarithm on both sides. So n naught will be 3504. D part. Explain a precaution necessary when handling a sample of an alpha emitting isotope. So use a tongs because alpha particle can travel only few centimeters in air, so you should keep it far away from you, little bit 5 centimeters away from you. So use tongs since it can travel only 5 centimeters in air. So that's the answer. Use tongs since it can travel only 5 centimeters in air. That's the answer for part D. Okay, question number 19. Microwave ovens use microwave radiation at a frequency of 2.45 gigahertz to cook food. The absorption of microwave energy by water in the food causes a heating effect. The graph shows how the energy absorbed by a water molecule depends on the frequency of radiation. So the graph is given y-axis energy absorbed and the x-axis is the frequency of the radiation. A website suggests that the water molecules absorb energy because the microwave produced by the oven caused the water molecules to resonate. Comment on this. You can see the maximum energy absorption occurs at almost 10 gigahertz, which is much greater than the frequency of the microwave. So actually here the driving source or the frequency at which the water is driven, also the driving frequency or the frequency of the driver, that is the frequency of the microwave, which is 2.45 gigahertz, which is not equal to 10 gigahertz, the 10 gigahertz at which maximum absorption is occurring. So actually resonance is not happening. So question number 19, A part. I am not writing the answer, very simple answer. You can say the energy is absorbed at, the maximum energy is absorbed at 10 gigahertz and it is not equal to the driving frequency. Within bracket you can put frequency of the microwave 2.45 gigahertz. Therefore resonance is not happening. Okay, so B part, the microwave radiation causes the water molecules to rotate. So here they are telling it rotate, not vibrate. It makes it rotate. That's called dipole rotation. So what happens during the rotation? The frequency at which they naturally rotate is 2.5 gigahertz. So there resonance happening. So when it rotates, what happens? The molecules will hit the other molecules, and due to collision, kinetic energy will be transferred. When the kinetic energy is transferred, what happens? Internal energy will increase due to collision. Energy is transferred and internal energy will increase. That's the reason the heat will be formed and the temperature increases. Question number 19, part B part, second part, suggests why the transfer of energy from the microwaves may be less efficient for ice than liquid water molecules. So you can say liquid, the ice is a solid where the molecules are rigid and difficult to rotate. They won't rotate, so they won't hit the adjacent molecules. That's the reason. So you can say the ice is a solid state. In solid state, the molecules are rigid and difficult. They won't be able to rotate easily. Therefore, they won't be able to hit the other molecules and transfer the heat is not possible. So it's maybe difficult. So that's the reason less efficient. Okay, part C, 325 gram of water at 25 degrees Celsius is heated at full power in microwave oven. After 225 seconds, the temperature of water is 85 degrees Celsius. Power of microwave oven 650 watts. Specific capacity of water given. The manufacturer claims that the microwave oven has efficiency of 90%. Assess the validity of this claim. So we can say heat absorbed by water is equal to E equal mc delta T. So I can say for water, the heat absorbed equal mc delta T. So E is equal to, so mass of the water 0.325, so 325 gram, convert to kilograms. Specific capacity is given as 4190, and the temperature change is given as 85 from 25. So the energy will be 81,705. So this is happening during 225 seconds. So power absorbed by the water 81705 divided by 225. So that will become 363 watts. So this is the useful output power which is absorbed by the water. So efficiency, input power also given. Useful output power 363 divided by input power is 650 into 100%. So that's going to be almost 56%, less than 90%. So invalid claim. By the manufacturer. Okay, question number 19, second part, C part, second part. The 325 gram of hot water at 85 degrees Celsius is poured into a polystyrene beaker containing 62.5 gram of ice at 0 degrees Celsius. So it's at 0 melting point. Calculate the final temperature of the mixture of water and melted ice. So we take all the ice melted into water. Latent heat of fusion of ice is given. Specific capacity of water is given in the previous page, which is 4190. So here what's happening when you pour water? So actually ice is at 0 degrees Celsius. So what will happen? Water will lose heat. So ice will absorb heat from water, and when the ice absorbs heat from water, first the ice will melt at its melting point. All the ice will be melted. When ice melts, it becomes water at 0 degrees Celsius. Then the water will reach the final temperature. So finally, everything will have the same temperature. So here we assume the container won't absorb any heat. So here we can say heat lost by hot water is equal to heat gained by ice during melting plus heat absorbed by the ice water. Ice water means the ice, when it melts, it will become water at 0 degrees Celsius, ice water, to reach the final temperature. Finally, all will have the same temperature. So I can say heat lost by hot water equal heat absorbed by ice during melting. So now it has become water at 0 degrees Celsius. Then it's going to absorb heat absorbed by melted ice. So ice has melted fully and has become water. Melted ice water to increase the final temperature. So heat absorbed by hot water, I can say mass of the hot water MW, CW. It was initially at a temperature of 85 degrees Celsius. Final temperature will take it T. So 85 minus T. This is the heat lost by hot water MC delta T. Delta T is initially it was at 85. Final temperature at steady state I take it as T. That is the question, I need to find it. Now heat absorbed by the ice during melting, the mass of ice which is melting into latent heat of fusion. Now this ice has become water at 0 degrees Celsius. So Mi, same ice, same mass of water. Now it has become water, same mass. Cw, now it has become water. Now it's at 0 degrees Celsius. It's going to reach the final temperature T, T minus 0. That's all. So substitute the values. Everything we know, we need to find the T. So mass of water we know that's 325. So 0.325. Specific capacity of water is given as 4190 times 85 minus T equal. Mass of ice is given as 62.5 grams. So divide by 1000 to convert to kilogram. It will be 0.0625. Latent heat of fusion of ice is given 3.33 10 to the power 5 plus mass of ice, actually it has become water now, water same mass as the ice, 0.0625. The specific capacity of water is 4190 into T. Okay, I need to find the T, that's all. So solve it, you know how to multiply inside and bring everything. So no marks for those step by step. So finally you will get 1623.7 T equal 94936.25. So T becomes 58.5 degrees Celsius. That's the final steady temperature. So here we assume, in case if they ask what assumption we made, we assume the container, the polystyrene beaker is not absorbing any heat. If the specific capacity of the polystyrene beaker and the mass of the polystyrene beaker also given, then we should put here plus heat absorbed by polystyrene here on the right side. We had to include it, but here nothing mentioned, so we assume it's not absorbing any heat. Question 20, that is question 20 is about simple harmonic motion. A part, state the conditions for a mass to undergo simple harmonic motion. That every year that question is asked. So we can say first one, the acceleration is directly proportional to displacement, 1 mark. Then always the direction of the acceleration should be towards the equilibrium point. First one, acceleration should be directly proportional to displacement. Second one, always the acceleration should be directed or point towards the equilibrium position. That's a second mark answer. Right, so B part, 250 grams is hung from the spring as shown. The spring extends by 16.5 centimeter when the mass is added to the spring. So that is the static extension. When you just add the mass, it extends 16.5 centimeter. So by using unit 1 idea, Hooke's law, F equal K delta X, we can find the K here. But anyway, the question B part is calculate the maximum kinetic energy of oscillation. So what's happening? The mass is then displaced a further 3.5 centimeter vertically downwards and released. The mass oscillates with simple harmonic motion. So what's happening here? The mass is initially, this is the actual position, natural length. When you add a mass, it extends. So this is the static extension. This is the static extension. That is how much? 16.5 centimeter. So this is the equilibrium position because it's at rest. This is the equilibrium position. From this position, because it's at rest, where the particle comes to rest, or when it is not oscillating, or the point at which the resultant force 0 is the equilibrium position. So this is the equilibrium position. Now from this position, they are pulling it further down through 3.5 centimeter, and release means the amplitude of oscillation will be 3.5. In a spring mass system oscillation, whatever the length or extension you produce from the equilibrium position, that is going to be the amplitude of oscillation during the oscillation. So now what's happening is released further down from this position. So this is going to be the amplitude of oscillation. That is, I'll put it here, amplitude is going to be 3.5 centimeters. That's the amplitude of oscillation. Okay, so this is the equilibrium position where I put dot dot. Okay, so first part, anyway, they asked me to calculate the maximum kinetic energy. We can do in two different methods. So method one, I'll do. Maxim is giving only one method. I'll do the first method, question number 20, B part. First method. Second method is not given in the mark scheme, I think, but you can do the second method. We can do. It's a correct one. I'll do that. So method one, I can say at equilibrium position. I can say F equal K delta X. That's a Hooke's law. Force, we know the mass which is attached, 250 grams. So that's a mass here, 250 grams. So that is 0.25 into 9.81 equal K times the static extension 16.5. So 0.165 meter. Find the K. So K will be 14.86 Newton per meter. Right. So I need to find the maximum speed. Maximum speed is V max equal A omega, omega equal 2 pi over T. I need to find the time period of oscillation. So T equal 2 pi square root of M over K, even in the data sheet. Mass is 250 grams, 0.250. Over K, we found it 14.86. So the maximum time, the time period of oscillation is 0.815 seconds. Okay, so I need to find the V max. V max equal A omega. A, we know that 3.5 centimeter, I need to convert to meter. Omega equal 2 pi over T. Substitute. So 0.035 into 2 pi over T, we found is 0.815. So the maximum speed will be 0.270, you can say 0.270 meter per second. Now they asked to find the maximum kinetic energy. So Ke max, that happens at the equilibrium position, because maximum speed occurs at the equilibrium position. So acceleration is at the extreme position, maximum, but maximum speed occurs at the equilibrium position. So the kinetic energy maximum also will be at the equilibrium position. So Ke max equal half m V max squared. Okay, so half, the mass is 0.250. And V max 0.270 squared. Solve it, you'll get the answer. So that is 9.11 10 to the power minus 3 joules. Okay, method 2, what I'm going to do, anyway I need to find the spring constant, but I'm not going to use the period or even V max square, anything like that. I'm going to use the law of conservation of energy. I know the maximum kinetic energy occurs at the equilibrium position. So it moves from the lowest position to the equilibrium position. It will have the maximum kinetic energy. So what energy changes occurs when it moves from lower position to the equilibrium position? It's moving up, so it's gaining gravitational potential energy, mgh. It's the gaining gravitational potential energy. So when it is gaining gravitational potential energy, mgh, h is this much. This is the h. So how much is the h? 3.5 centimeter is the h. I need to convert to meter. So it's gaining GPE when it moves from the lowest position to equilibrium position. So I'm going to consider the motion from lowest position to equilibrium position. I'm going to find the energy, the kinetic energy at the equilibrium position. So it's gaining gravitational potential energy. Then its speed is increasing at the lowest position. That's the extreme position. The speed is 0. Here the speed is maximum, so it's gaining kinetic energy also. So when it moves from the lowest position to equilibrium position, it's gaining both GPE, that is gravitational potential energy, and kinetic energy, both gained. So what is lost? The extension of the spring is decreasing. So at this position, at the lowest position, the extension of the spring is 16.5 plus 3.5, that is 20 centimeters the extension. So due to that extension, it has elastic potential energy, half k delta x squared. Unit 1 you learned that, half k delta x squared. So at the lowest position has the elastic potential energy, half k delta x squared, where delta x is 20 centimeter, convert to meter, square it. Then at the equilibrium position, still it has elastic potential energy, which is due to the extension of 16.5 centimeter. So it's losing the elastic potential energy. Elastic potential energy at the lowest position minus elastic potential energy at the equilibrium position is the loss in EPE, equal to gain in kinetic energy plus gain in GPE. From that I can find the kinetic energy at the equilibrium position, that is the maximum kinetic energy. So I can say loss in elastic potential energy, EPE, equal gain in kinetic energy from 0 to maximum at the equilibrium position, plus gain in gravitational potential energy. I am going to consider the motion from lowest position to equilibrium position. So loss in EPE, elastic potential energy, half k. At the lowest position, the extension let it be delta x2 squared minus half k delta x1 squared at the equilibrium position is equal to gain in kinetic energy, half, I can say gain in kinetic energy means final kinetic energy at here, that is the maximum kinetic energy. Here the kinetic energy is 0 at the lowest position. So Ke max minus 0. I am considering the motion from lowest to equilibrium position, plus gain in GPE, that is mgh. H is anyway I am going to put 3.5. I will put mga. A is the amplitude, which is 3.5 centimeter. That is the h. Okay, so half k I can take common. Half into k is 14.86. Delta x2 square. Delta x2 square is 16.5 plus 3.5, that is 20 centimeter, convert to meter, 0.20 squared minus delta x1 squared at the equilibrium position, because I am considering the motion from lowest to equilibrium, because I know the maximum kinetic energy occurs at the equilibrium position. So at this position the extension is 16.5, so 0.165 equal Ke max I need to find, minus 0, leave it. Mass is 0.250, 9.81 into A, the height it moved is 0.035. That's all. All numbers, find the Ke max. You'll get the same answer. So you'll get 9.1, 10 to the power minus 3 joules. Same answer, you will get it. So here I am not using the equation for period t equal 2 pi square root of m over k. I am not using. Then V max equal a omega. That also I am not using here. Just conservation of energy. but not given in the mark scheme. So the 20th question, part C. The graph shows how the displacement of an oscillating mass varies over 2 cycles. Uh, add to the graph to show how the kinetic energy of the mass varies over the same time. You know that when the displacement is zero, where equilibrium position, the kinetic energy will be the maximum, and kinetic energy is always positive, it's a scalar quantity. So at this position, kinetic energy is maximum. When the displacement is maximum, that is the extreme position where the speed is zero, kinetic energy is zero. So here kinetic energy is zero. Again, when the displacement is zero, equilibrium position, kinetic energy is maximum. So here negative displacement means extreme position where speed is zero. Again, this is maximum, this is zero, maximum. So the graph will be so it will be double the frequency, always on the positive side, because kinetic energy is always positive. It's a scalar quantity. Okay, same question, part D. The mass is submerged in water as shown. So they are keeping the mass inside water. The mass is set into oscillation as before. Explain how water would affect the amplitude of oscillation of the mass. So you can say due to viscous drag force, the mass will experience opposing force. So the oscillating mass will lose its energy to the surrounding, or the energy will be removed from the mass. Therefore, amplitude of oscillation will gradually decrease. That's the answer. Okay, so I hope you understood this paper discussion. So very soon I'll upload a video related to complete revision on cosmology, and if possible on oscillation also. I hope it will be useful to you. Okay, bye.